Madam Rosmaya. In this video, we are going to discuss on nuclear binding energy. So what is nuclear binding energy? So we have discussed before the meaning, the definition for nuclear binding energy. The occurrence of nuclear fission and fusion can be explained in terms of the binding energy per nucleon, which is the binding energy of a nucleus divided by the number of nucleons in it. Okay? So this is the equation for nuclear binding energy per nucleon. So nuclear binding energy of the nucleus divided by number of nucleons in it. Okay, refer to the graph of binding energy per nucleon against mass number. Okay, this is the highest point. It's in the group of iron group. Okay, iron group here. So what does this mean at the nuclei with high binding energy per nucleon? So this means that they are very difficult to break up. Okay, the nuclei are very difficult to break up. So isotopes of the iron group have the highest binding energy per nucleon, and hence they are the most tightly bound nuclei. Okay. So this explains why there is an abundance of the iron group elements in the universe. Okay, so for the group of mass number 40 to 80, okay, nuclides with the mass number 40 to 80, so these are considered as stable, okay, and they means that they have a relatively high binding energy per nucleon. Okay, another means like mentioned just now, that means a great amount of energy is needed to break up these nuclides. Okay, nuclides to the left here and right of the iron group have lower binding energy per nucleon, and they are said that they are less tightly bound. Okay, thus less energy per nucleon is required to break them apart. Okay, left side and right side here. Okay, so we are going to compare energy release in fission and fusion. Okay, so for fusion is this part. Okay, the left part of the curve suggests that a pair of light nuclides can be combined to form a single heavier nuclide that lies nearer to the iron group to achieve higher stability. Okay, so this is light nuclide. Okay, maybe one or maybe two or more nuclide combined together, fused together. Okay, to get a single heavier nuclide. Okay, and it's nearer to the iron group. Okay, such a process called fusion, okay, and occurs naturally in stars. Energy is released during such process. Okay, for the right side, right part of the curve suggests that if a heavy nuclide were to split into two nuclides that lie near the iron group, here split into two nuclides, so towards to the stable nuclides here, the arrow of the line drawn here. So this means resulting nuclides would be more tightly bound. Okay, such a process is called fission, and it involves the release of tremendous amount of energy too. Okay, from the gradient of the curve left and right side, okay, from the binding energy per nucleon curve here, okay, we can see that the left part of the curve has a much steeper gradient compared to the right part of the curve. Okay, thus it is clear that more energy per nucleon is released in a nuclear fission than that released in a nuclear fission. Okay, so the steeper the graph here compared to the right side, so that's mean in nuclear fission release higher energy, okay, compared with the fission. Okay, so mathematical, we can determine the energy release here is equals to the total binding energy minus total initial binding energy. So the energy released by fission of a high mass nuclide can be estimated by considering the total binding energy of the nuclides before and after the fission. Okay, so we try one question here. Assume that a high mass nuclide such as uranium-236 splits into two equal fragments, each of mass number 118. So 118 plus 118 we get 236. Okay, so we assume two equal fragments with mass number 118. Okay, from the curve we are going to estimate the binding energy per nucleon of uranium-236 and also its fission fragments. Okay, from the graph here, for 236 we read from the scale x-axis. The reading on the y-axis, the binding energy is about 7.6, and at 118, mass number 118, we get about 8.6 mega electron volt. Okay, so this is the reading from the y-axis. The binding energy per nucleon of uranium-236 is about 7.6 mega electron volt, and its fission fragments is about 8.6 mega electron volt. Okay, so we are going to do the calculation for binding energy, total binding energy before and after. So before it's in the form of uranium-236. Okay, so we read directly from the graph to 7.6 mega electron volt. So the total binding energy is 236 nucleon, and the graph is per nucleon, means one nucleon. So for 236 nucleon number, so times 7.6, you get 1793.6 mega electron volt. Okay, this is total binding energy before it's before the fission process. Okay, the fragments has per binding energy per nucleon 8.6 mega electron volt. So the fraction has 118 nucleon number, but two fragments, so again times 2, and then times this 8.6 mega electron volt. So the total binding energy, the fission fragments, is 2029.6 mega electron volt. Okay, so the difference between these two binding energy is 236 mega electron volt. Okay, 2029.6 minus 1793.6, so we get 236 mega electron volt. So this is the energy release. So the energy release per nucleon, so you divide it by the number of nucleon of uranium is 236. So this 236 mega electron volt divided by number of nucleon U236. So U236 divided by 236, we get 1 mega electron volt. So this is the energy release per nucleon. So we keep this value for a while because we are going to compare with the energy release in fusion. Okay, similarly, the energy release in single fusion process can be estimated. Okay, so we try this one for mass number 5. Mass number 5. So the reading we get from the graph here. And also it combined together, fused together in the fusion process to get mass number 10. Okay, heavier mass. Okay, so from the graph here, 5 somewhere here, the reading is 2 mega electron volt, and for 10 mass number A, 10, so we read here is about 7. Okay, so 2 mega electron volt and 7 respectively, reading from the graph. Okay, now we are going to calculate the energy release. So the total binding energy before it is fused together, okay, for per nucleon is 2 mega electron volt. So the 2 mass before it's fused together, so 2 times 5 times 2 mega electron volt. So we get 20 mega electron volt. Okay, so the two light nuclei, okay, we fuse together. This is before they fuse together, and their nucleon number is 5. Given mass number is 5. So 5 times 2 times 2.0. So next is the after fusion. This is supposed to be fusion, not fission. Typing error, okay, typing error. So this is fusion process, okay. So the after fusion, it becomes heavier nuclide with 7 mega electron volt energy. So the total will be times 10 because the mass number is 10. So that's mean 10 times 10.0 mega electron volt. So we get 7 mega electron volt. So now the difference is 70 minus 20. So 50 mega electron volt energy is released. Okay, 50 mega electron volt energy is released. So per nucleon, so you divided 50 to mass to 10. Okay, 50 divided by 10, the product is 10. The mass, the heavier nuclide form has 10 nucleon number. So divided by 10, so you get 5 mega electron volt. Okay, so now compare with the previous, we get in fission, energy release in fission is 1 mega electron volt. Compare with the energy release in fusion, 5 mega electron volt. So that's mean more energy per nucleon is released in a nuclear fusion than that released in the nuclear fission. Okay, so that's all for the discussion today. Okay, thank you for watching.